So what do we do first on these? You must first find the ratio of lengths. And that's going to be 12 to 20 or reduced to 3 to 5. Good. Now let's look at the surface areas, which of course is just an area, right? How do we get that ratio of areas from the ratio of lengths? We square it. So that becomes 9/25. 3 squared is 9, 5 squared is 25. And where does the 450 go? Top, because it's the smaller one. We'll cross multiply and divide to get 1250.
You got it.
Good deal. Oh, that. There, that's probably better. So now we're going to do it for the volume. We're going to do a 3/5 and we're going to cube it. So that'll be 27 over 125. And then the 675 goes on the bottom. Cross multiply and divide to get 125 or 45? 45. What do you think? Good stuff?
No.
Richard's pretending to be happy over there, so we'll move on and do something else.
Yeah, what do you want today? What do you want today?
Well then, just to make Richard happy, we are going to move on to something new today. We're going to be back in that packet you guys looked at, had the measurements on front. We just did the first page of it, and then we paused there. Yep, we're adding and subtracting measurements in the front page. Yep, yeah, we gave it to you way back, like the second day class. That one. So we're going to be looking at some aspect ratios and stuff like that today, dealing with tapers and slopes and all sorts of good stuff. But we're going to look at just a simple aspect ratio at first. An aspect ratio is often used to describe a sloped surface of some sort. Pretend all these lines are straight, even this one here. It does run at an angle. Let's say I'm given dimensions like 20 centimeters, 28 centimeters, 12 centimeters, and then given this. That's a 2 to 3 aspect ratio. What does that mean? Well, that means for every 2 units it goes up, it goes over this way 3 units. Or the other way around, for every 3 units it goes over, it goes up 2 units. Either way. So what that means, I can draw a triangle in here, either down here, or I could draw it out here. Either one would have worked. Do I know either of those 2 dimensions? Yes, I do. I know this one right here. How? 20 minus 12 makes that 8 centimeters. Any questions where the 8 came from? So now to figure out this dimension, I can use that dimension in the aspect ratio. I'm going to put 2 over 3. I always put vertical over horizontal, rise over run, because that's what I'm used to. But you can put them either way. The key is here, the 2 is vertical, the 8 is also vertical, so the 2 and the 8 have to go together. And now I can cross multiply and divide. I get that this is 12 centimeters. So So this is 12 centimeters. And that means this must be 16 centimeters. Make sense? So we can have some more complex problems like this. Where I ask you to find x. Oh, what do I want to put in there now? See if you can find x for me in your notes quick. What'd you come up with so far? 21, you say? Excuse me. So look at those two dimensions. Do I know either of them? Oh, the horizontal. Well, how do I find that? 72 minus the 24 and the 20 would be 28, right? So then, yeah, 3 over 4, where's the 28 go? Bottom, because it's horizontal. So it has to go with the horizontal, which is the 4. 28, yes. Thank you. Cross multiply and divide gives us 21. So those aspect ratios are relatively simple to work with. Now we want to talk about something called a taper. A taper is a more specific aspect ratio that rather than just relating a rise and a run, a vertical and a horizontal dimension, it actually relates a diameter, more specifically a change in diameter to a length. And a taper is defined to be change in diameter. That little triangle is the delta symbol that says change in, is what it's the abbreviation for. Change in diameter in inches to length in feet. So for example, let's say I have a 0.25 inch per foot taper. What that is saying is, if I have a round piece that's tapered, notice the diameter is changing over the length of that round piece. If it is 12 inches or 1 foot long, the diameter changes by 1/4 inch. So let's say I know that this is a 2-inch diameter, this will be 1 3/4 inch diameter. Or 1.75 inch diameter. Does that make sense? Your formula, your taper is big D minus little d over length divided by 12. Why is there divided by 12 in the bottom? Converting the length into from inches into feet. Very good. So let's say we have a piece of tapered round stock that is 18 inches long. It's 1 3/4 inches here. And let's say that it is, let's go 1 1/2 inches here. Not 1 1/2, but just a 1/2 inch here. Find the taper. Well, I'll walk you through this one and I'll have you try another one in a second. So it's 1 3/4 is big D over, or minus 1/2 is little d over 18 divided by 12. So 1 3/4 minus 1/2 is 1 1/4. 18 divided by 12 is 1 1/2. We divide that out, and that is 5/6, or 0.8333 inches per foot in our taper. Is that what you guys come up with? Sure. One 3/4 minus 1 1/2 is 1.25. 18 divided by 12 is 1.5. 1.25 divided by 1.5 is 0.8333. Let's take a funnel, or the cone of a funnel, or the frustum of a funnel, I should say. It doesn't come to a point, so the frustum of a funnel. It goes from 8 inches, tapers down to a 1/2 inch in a 9-inch run. Find the taper of that. Do that in your notes for me. There he is. Okay, so tell me how you plug this in. Eight minus just 1/2, right? Nope. So that's 7 1/2 over 9 over 12, which is 3/4, and then 10 over 1. So that's 10 inches per foot of taper. Good stuff. Now there's something, I don't know if you've talked about them in the shop yet. There's something called Morris tapers. You've heard about them? They're standard tapers that are used. Morris tapers are almost barely detectable. They're so slight. Like the standard number 4, I don't even have it memorized anymore. The standard number 4 Morris taper is 0.62326 inches per foot is all it is. So that's inches per 12 inches. So you can see that's just over 5 or just under 5/8 of an inch in a foot. It's not a lot of taper. So anyway, other things that we're going to be dealing with is we're going to be dealing with our pulleys. We've talked about this before. Let's say we have a 6-inch pulley that is running at 360 RPM. It's attached by a belt to a 9-inch pulley. How do we figure out how fast that 9-inch pulley is going? As the pulley gets bigger, the RPMs get smaller, right? So this is an inverse relationship. So we don't use the proportions anymore. We use the products. So size times speed, 6 times 360. Has to equal 9 times whatever that RPM is. So you multiply the 6 times 360, divide by 9, should get 240. So this will be 240 RPM. One that I want you to try in your notes, see how you do. I want you to find the RPM on that 6-inch pulley. If (800 RPM on the 4-inch pulley. Try that in your notes. See what you come up with. Know what you did? Cool. Never mind.
Never mind. No,
Let's say a peak. So we're going to find the RPM of the 10-inch one first. So it'll be 4 times 800 equals 10 times blank, right? You get 320 RPM for that. How do we find out how fast the 3-inch one is going? Probably the same because they are connected on the same shaft. So they're not the only time this relationship holds is if they're connected by a belt. If they're on the same shaft, they have to turn the same RPM. So to get the 6-inch one now, it's the 3-inch times 320 equals 6 times blank, and that's going to come out to be 160 RPM. So some of you are right. Any questions on how that works? Okay, well, we are going to do a lot of work time today. Okay, so the one other example that I wanted to show would be like a scale drawing, which you guys have seen, but I wanted to make sure you're aware. Like, say, we've done like a 1 in 32 scale, 1/32 scale drawing. Just means that it's drawn 1 unit for every 32 actual units. So if something's drawn on the paper at 1 1/4 inches, I don't know where all this crap's coming from. What is it in real life? Well, it's 1/32 equals 1 1/4 over x. So 32 times 1 1/4 is 40. So it's actually 40 inches in real life. But something you run into if you're doing something large, usually this is more architectural than mechanical drawings, but you might run into a 1/8 scale. A 1/8 scale is actually 1/8 to 1 foot, 1/8 inch to 1 foot. So to do that scale, we can't do 1/8 inch to 1 foot. Well, we could. We do 1/8 inch to 1 foot. That's now a rate rather than a ratio. And let's say we have something that's drawn 1 1/4 inches. We can cross multiply and divide. 1 times 1 1/4 divided by 1/8 is 10. That's going to be feet. Because the units here are feet. It's usually less confusing if I do this. 1/8 inch to 12 inch. Now it's a ratio. By 1 1/4 inches there. Then when I cross multiply and divide, I get 120 inches here that I have to convert back into 10 feet. Usually less mistakes are made that way. But when you deal with the scale drawings, just make sure you know whether I'm comparing inches to inches or inches to feet when you're doing your scale. If you look in the fine print, it'll be a 1/8. It'll be 1/8 inch to 1 foot somewhere. But they just refer to it as the 1/8 scale. And if you got one of the little tri-rulers, scale rulers, it'll just say the 1/8 scale on it. It won't say 1/8 to 1 foot.
You'll might see more 3 to 1 or 4 to 1.
You guys are going to see a lot of 1 to 8, pure 1 to 8 scales rather than a 1/8 to 1 foot. You'll see like a 1 to 4, 1 to 8.
We make some small parts where I work from home. Part bigger on it.
Oh, you mean blown up? Yeah. If you got some really small parts, you might actually see a reverse scale where it's a 3 to 1 or a 4 to 1. Sometimes even I've seen it up to 6 or an 8 to 1. We have it up on the big blueprint paper. Yep. Okay, so in this packet, I want you guys to try to get up to, we'll do from problem 31 to 43. We are going to skip problem 44, just so you know. '44 and 45 are going to be extra credit if you want to do them. If you can get me the right answer for them. They're not terrible fun, I swear. So I'll give you guys the last 20 minutes to get working on those.